Hey everyone, good evening, guys. Perfect. So let me quickly share my screen and we can get started, guys. Okay, a quick check. Voice is good, screen is visible, everyone. Awesome. Okay, so we have done all the feature engineering and everything. PCLD and all. Today we will be starting with the linear algorithms. Okay, so we'll be discussing the all possible concepts about the linear algorithm like linear regression, how does it work, how will it get trained, what are the parameters, how the parameters will be finalized, right? What are the problems we face in linear regression and all those things. So we'll talk about everything in linear algorithms. When to use fit and when to use fit transform in PC and LDA. Good question. Good question, guys. See, when do we need to use fit and fit transform? Whenever we say fit, it will analyze the data. Whenever we say fit transform, it will transform the data. So remember the concept of train test split, right? Remember the concept of train test split? Yes. So in train, we will do fit and then transform, right? But in test, we only need to do transform because transformation should this transformation should exactly be similar as per the train data statistics. So this is what we need to keep in mind. While we have the test data, we don't need to fit for the test data. We need to transform only for the unseen data, but whatever we have the train data, we need to fit and then transform it, right? Perfect. Now, yes, sure. See, we know the concept of train and test data. So whenever we have the train data, we need to do the fit and transform both. Fit is basically fit function will try to analyze the data statistics and everything, and it will see how what kind of what number of principal components needs to be created, needs to be transformed in a given data set. So we need to do fit on the train data, and then after fitting we need to transform on the train data. But when it comes to the test data, we will only transform on the same object that has been fitted on the train data, right? So for test data transformation, we don't need to create a new PC object and fit it again. We will be using the same fitted object that we have used in train data and just transform the test data. Okay. No, scaling should be definitely, if scaling is there, we need to do the scaling. Whatever we do in train, exactly all those steps needs to be done on the test also. Otherwise, our model will not be able to perform well. The scaling needs to be done. Whatever pre-processing we have been doing in the train, exactly those pre-processing we should do on test. But make sure the analytical part, the thing what we analyze on the train data, that is something we can't do on the test data, because test data is something unseen. We kept it aside, so we should not analyze it. We are considering that data. This data will come in real time, so we cannot analyze the real time observations. So what analysis, what insights we understood, what we carry out in the train data, exactly same concept, same insights, same steps we need to implement on test data without any analysis. Make sense? Perfect. Let me erase this now and let's start with the linear stuff. Perfect, guys. Now, linear algorithm. First of all, what is the equation of a straight line? Anyone? Do you know what exactly is the equation of a straight line? Y equals to mx plus c. Yeah, we can discuss it in Q&A. Y equals to mx plus c. Right? Now, if we try to represent this y equals to mx plus c using a figure, this is the x-axis, this is the y-axis, and if there is a line like this, we can represent this line as a y equals to mx plus c, right? Y equals to mx plus c. Now what exactly is m and c, guys, here? What do we understand by m and what do we understand by c here? Anyone? M is slope and c is the intercept. M is slope and c is the intercept, correct? So if I tell you this angle theta, so m equals to tan theta, right? And this distance is called c, right? Perfect. Now this is as per the mathematics. This is as per the mathematics. Let's pick a business case and try to understand from that business example. Suppose X is the advertisement amount, okay, on a given product, and Y is the sales, right? So the equation will become sales equals to M into advertisement amount plus C, right? Yes, guys, that will be the equation in that case. M into advertisement amount plus C. Sales can be calculated using this formula. Yes, guys? Okay. Now, from this equation, what do we understand by M and C? What is M and what is C in terms of sales and advertisement, guys? Not in terms of mathematics like slope and intercept. What do we understand the M and the C in terms of sales or advertisement? C is a constant, but okay, what that constant represents in sense of sales or advertisement? I mean, the multiple factor of advertisement. Yes, yes. M is actually the increase in sales per unit, increase in advertisement, right? M is the increase in sales per unit change in advertisement amount, right? Or the change in sales per unit change in advertisement amount, right? That's the M. C is the sales when zero advertisement. Exactly. Exactly, guys. So M is the change in sales per unit change in advertisement, and C is amount of sales with zero advertisement, right? Right? Understood till here, everyone? As per this basic linear equation, y equals to mx plus c, where we have two factors, sales and advertisement, where we are trying to calculate the sales with the help of advertisement. So we have this equation, sales equals to m into advertisement amount plus c, where m represents the change in sales per unit change in advertisement amount, and C represents the amount of sales with zero advertisement amount, right? Clear, everyone? So we understood what is this M and what is the C from the mathematics as well, and also from the business terms. How do we interpret the value of M and the C, right? Okay. Now let's see how exactly this mathematics can be helpful in machine learning. We discussed in machine learning, we try to make the machines learn in order to make the to make the predictions on unseen data, right? Yes. We know in machine learning, we try to make a machine learn in order to make the recommendations, in order to make the predictions on new data, unseen data, right? That's what we do in machine learning. Now let's see how this can be helpful in machine learning. How this can be helpful in machine learning. Suppose we have the sales and advertisement data for some company, right? So for some product-based company, so they have a lots of different products. They have the advertisement amount they spend and the sales they get, right? Suppose this is the data. Now we need to build a model. We need to build a software that can train on this data and can tell us what's going to be the estimated sales on new products for a given advertisement amount, right? Right now, we have the advertisement amount and sales for some products. Let's say there is a new product that is going to be launched. So let's suppose we plan to spend some XYZ amount of advertisement, and we expect from machine to give us estimated sales on that. So that could be a possible implementation of machine learning if I plot a flow chart. So we have sales and advertisement amount data, consider it as a trained data, to some machine learning model, right? Machine learning model. It will learn, right? Now once it's learned, we can simply give the advertisement amount and it can predict the sales, right? Predicted sales on a given advertisement amount. Now this is unseen data, right? This is unseen data. Possible? A possible application of machine learning in this case? Sure. We have the sales and advertisement as our training data. We gave the sales and advertisement data to some machine learning model. It will learn, the machine learning model will learn to predict sales on a given advertisement amount. Now on this learned model, if we give advertisement amount, this learned model should get us the predicted sales, right? Let me write it clearly. Yes? Make sense? Once the model is learned, we can give the advertisement amount that is unseen. Right now, the model have not analyzed this specific value of advertisement amount, but the model should be able to predict the estimated sales on this given advertisement amount, right? Right? Make sense, everyone? Awesome. Okay, so now the equation is clear. How we can use this equation for the machine learning, this is also clear. Great. Learn is unseen data. Learn is not unseen data. It's a learned model. It's a basically learned model, right? We will give unseen data to this learned model and this model will give the predicted sales. It's not the unseen data. We are giving some unseen new advertisement amounts and this learned model, this is actually model, learned model will predict the sales on a given advertisement amount. Yes, this is unseen. Got it? Perfect. Perfect. Okay. Now, if we observe this equation, now we see in a practical case, in the case of a practical problem where we have the sales and advertisement and we want to get the predictions on sales for a given advertisement amount. So In this equation also, we are going to have the sales values and we are going to have the advertisement values, right? From this equation, we are going to have the values of sales and advertisement amount, right? But we won't be having the M and the C. We won't be having the value of M and the value of C. We don't know what should be the good value of M and C. We just have the sales and we just have the advertisement amount, right? Yes, guys? Like we discussed about a problem, a practical problem where we have the data set, data about the sales and advertisement. We want to train a machine so that machines can predict the sales on a given advertisement, right? So actually we have the sales and advertisement amount only. We don't have the M and the C, right? So this learning state is the calculation of M and C only, right? While the model is learning on a given sales and advertisement values, it is trying to calculate the good values of M and C. That's the training phase. That's the training phase. Yes? Okay, now mathematically and from the business point of view, we have some data. We utilized that data to calculate the parameters that the parameters are M and the C. So we utilized the data, we calculated the M and the value of C, and then by the help of those M and C, we get the predictions. Easy? Understood the flow? Okay, now big question here is how do we calculate M and C? The big question here is how do we calculate M and C? Now we will discuss about that. How we are going to calculate the M and the C. Okay, so before we proceed, the training process, how the calculation of M and C will happen. Are we good with this overview? Like what exactly is linear algorithm? What is the mathematics? How we can relate all these mathematical terms with a practical business problem, and how this can be used as a machine learning, machine learning solution. Right now if the solution is not, if it's not linear, then we cannot use linear algorithms, right now we are discussing about the linear algorithms and we are considering that we have some linear correlation between the predictors and the target variable. Okay, now what is the target variable here? That is the sales. Right now we are trying to understand the linear algorithms, right now we are trying to understand the linear algorithms. So whenever we work with the linear algorithms, means we have some linear correlation between the factors, then only we are trying to get the predictions, trying to capture that correlation using linear algorithms. If there is no linear correlation, if there is not linear relationship, then we will go with some another algorithm. Okay. Yes, make sense? Make sense? We cannot actually see by the plots, to be honest. We cannot see by the plots while doing the linear regression, because in real time we used to have a huge amount of data. 30 columns, 40 columns, one target variable. So we cannot plot 31 dimensional data to see the linear correlation or not. Okay. Right? We will come to that part. Let's finish one by one, guys. Let's finish one by one. Let's not divert the topic. Let's finish this. We will talk about the pros and cons. How do we do everything, the data analytics, whether it's good or not. How do we do the feature engineering and everything. Let's do one by one. Yes. Okay. So as of now, is this thing is clear, everyone? Perfect. Perfect. Now, let's understand this MNC, because we need to calculate the values of MNC only. Okay. Let's understand what exactly is this M and C, because we need to calculate the value of M and C only. Now, suppose we have a data like this. I'm again just taking some hypothetical examples here. Advertisement, amount, and sales. Okay. Let me create a line also. Yeah, there are functions, but we need to know how those functions are working, right? There are definitely, we have the functions to calculate the values, but we need to know the process, how those functions are working. Okay, let's suppose this is the data and this is our best fit line, right? We have this data and this is our best fit line, or we can say this is the line, this is the linear relationship between sales and the advertisement, right? Right? So there are lots of lines possible. This is also a line possible. This is also a line that is possible, right? There are lots of such lines possible, but this green one is only the best. Yes? Yes, guys, there are lots of lines possible in this two-dimensional space, but only this green one is the best, right? And why this green one is the best? Because it is actually explaining the trend, or we can say it is actually explaining how the data is correlated. What is the linear relation between the sales and advertisement? That's why we say this green line is the best. Make sense? Okay. Now this green line has specific M and C. This green line has specific M and some specific C. If we change the value of this green line's M and this C, the line will get changed, right? If we change the value of M and C, this line will get changed, right? If we change the values of M and C, this line will get changed. So if we say we need to look for a best fit line, or if we say we need to look for a good values of M and C, that is the same thing here, right? Looking for a best fit line is similar for looking for a good values of M and C, right? Make sense? Yes, guys. So that is actually the same thing. Either we say we want to get a best fit line, or we say we want to calculate the best values of M and C. That is the same thing, because M and C are defining the lines. If we change the M and C, there will be a completely different line. So a best fit line is going to have the best values of M and C, and that's what we need to look for. Got it? So now the training process, what is the training process? Is to find a best fit line or to find a best values of M and C. We don't have MNC right now. We do not have the MNC. We need to calculate the MNC, right? We don't have the values of MNC right now. We need to calculate them. We don't have the line right now. We do not have the line. We need to look for the best fit line. We just have the sales and advertisement data, but now we need to search for what should be the best value of M and C, or what is the best fit line. Understood? Now what we need to do here is we need to look for the best fit line and we need to look for the best value of M and C. Clear? Perfect. Perfect. Now here in this plot, in order to find the best fit line, in order to find the best value of M and C, we need to know what is the best, right? We need to define what exactly is the best first. Then only we can go with the best fit line and we can calculate M and C, right? So the very first step is to define what we call as a best, right? Why we are calling this green one as a best and no other line as a best fit line? So first we need to define, we need to explain how exactly we are saying that which one is the best. Anyone which one is the best? How we can explain this green is the best? Why this green is the best? Yes, guys. Anyone? How do we say this green is the best line? What exactly we are looking for here as a best? No, we don't have MNC right now. Centralized distance represents most data. Okay, equal scatter both the sides, giving no outliers, least error, passes through lots of data sets. It should reach the maximum data. Excel relationship. Okay, correlation. Yeah, lots of close answers. Lots of close answers. Now there is a principle called OLS. There is a principle called OLS that will explain the best fit line. Mark this down. OLS stands for ordinary least square. Okay, there is a principle. OLS stands for ordinary least square that explains the best fit line. Now as per the OLS, which one is the best fit line? The line that has minimum distances from all the points. This distance from point to line, right? This distance from point to line, right? This distance from point to line, whichever line has the minimum sum of square of these distances should be the best fit line. So as per the ordinary least square method, it is simply saying the value of MNC that has minimum sum of square of all these distances, that should be a best fit line. So there are lots of lines. Calculate the sum of square of distances from that line. Whichever line has the minimum sum of square of distances, that is our best fit line. Make sense? Make sense? Yeah. Here we are trying to define what we call as a best fit line. Here we are trying to define what we call as a best fit line, right? So OLS is trying to explain what exactly is the best fit line, and as per the OLS, it is the line that has minimum distance from all the points. Minimum distance from all the points, and in order to calculate it, we calculate sum of square of distances. This distance plus square of this distance plus square of this distance plus square of this distance. So sum of square of all the distances will be calculated. Whichever line gives minimum value of sum of square of distance is the best fit line, right? It is the sum of square of distances, guys. The distance from a point to a line, the square of this distance plus square of this distance plus square of all the distances, that value should be minimum for a given MNC, and that's what we call as a best fit line. Okay? MSE is a error, mean squared error. OLS is a concept that tells what is the best fit line. Perfect, guys. Clear till here, everyone? Okay, so now we know what is a best fit line, right? Now we know what is a best fit line, right? Yes, and basically how we define the best fit line is the best fit line is the one that has minimum sum of square of distances, right? Clear? Awesome. Awesome. Okay, now let's see how do we get the best values of MNC. So first we need to have some equation, something to calculate the sum of square of distances, right? Okay, before we talk that, I have a small question here. Yes, guys, I have a small question here. Ideally, when we talk about the distance of a point to line, when we talk about distance of a point to line, Suppose this is the line, this is this is the point, right? So we calculate the perpendicular distance, right? Yes, distance of a point to line, we calculate perpendicular distance. But here we are not calculating perpendicular distance. Why so? Yes, guys, why here we are not calculating perpendicular distance? Yes, because of line means. Okay, now what will be the difference if we use perpendicular? Because we are trying to predict y. We want only change in y. Exactly, exactly, exactly. Because we want to calculate the difference in actual y. See, what does that mean? What does that mean? Let's say for this given advertisement amount, this is the actual sales, right? For this given advertisement amount, this is the coordinate and this is the actual sales, right? Yes, guys. Okay, but when we use this linear regression, here it will predict the sales and this will be the predicted sales. So we want this difference to be minimized between actual and predictions. We want this distance to be minimized, that is the actual and predicted values. That's why we are calculating this distance. Make sense? And not the perpendicular one, right? Sure, sure. For this given advertisement amount, let's consider this coordinate. This is the actual sales. On this coordinate, this is the actual sales for this advertisement amount, right? And if we make the predictions, here the prediction will lie. This will be the predicted sales, right? So we need to calculate the difference between actual and predicted sales. And we need to minimize the differences between actual and predicted sales. Correct? Yes, these lines are parallel to the y-axis. Correct, everyone? Awesome, awesome. So let's write a equation. So we can simply write it as a cost function. Cost equals to sum of I equals to 0 to n. Yi is our actual I minus mxi plus c is the predicted I whole square, right? That will be the equation to calculate the sum of square of errors for a given value of m and c, right? Right? We can use this equation to calculate the sum of square of errors on a given value of m and c if we have. But right now we need to look for the m and c. So this equation will work to calculate the sum of square of errors and we named it as a cost function, right? Yes, guys, we named it as a cost function that is trying to calculate the sum of square of distances. Understood this equation, everyone? Perfect. Perfect. Now, how do we calculate the MNC? This equation is simply calculating the sum of square of distances. So that's the actual y minus predicted y whole square and summation for all the values of I. This is actual y minus predicted y, the square of difference and sum it for all the values of I. I is the number of observations we have. Correct? Perfect. Perfect. Now, how do we get the best values of MNC? In order to get the best value, we have a optimization algorithm called gradient descent. So ultimately what we need to do, we need to optimize this function, we need to minimize this function by tuning the values of MNC, right? Yes guys, we need to optimize, we need to minimize this function by tuning the values of MNC, right? That's what we need to do now. We need to optimize or minimize this function value by tuning the values of MNC. For this function, MNC are the variables, x and y are the constants, because x and y are something related to the data and we cannot change them, but MNC's m and the c are something we can tune. So right now for this function, MNC are the variables and x and y are the constants. Make sense? Yes. So I can write it as a function of m comma c. Yes, I can write this. I can write it like this. It is a function of MNC, means this will change with every value of MNC, right? Awesome. Oh, sorry, del B square. Del B square. Del B square. Okay? There will be square. Okay, so right now we can say the m and c are the variables for this equation, because the value of this equation will keep on changing with the different values of m and c. We cannot change x and y because they will be the constant. We have the data points and we cannot change the data points. So m and c will be the constants. Sorry, x and y will be the constant. M and c are the variables for this function. So that's why we have written it as function of m and c equals to this. We change the value of m and c, this function will change. Correct? And we need the derivative. Yes, yes, yes. Yes, clear? This function? Everyone? Okay, now there is an algorithm called gradient descent. Both equation are same. Yes, we simply wrote it as function of MNC because the values will get changed. Value will vary with the different values of MNC. That's why we have simply written it as a function of MNC. Perfect. So now we have algorithm gradient descent, that is basically for optimization or minimization. Optimization. And what this algorithm actually does, it will try to work with the derivatives in order to change the values of m and c to minimize these functions. Okay, so in order to understand this in more detail, we need to understand the derivatives first. We need to understand the derivatives. Now let's see what are derivatives. Yeah, let's see the derivatives now. So let's assume some function or any random curve. Okay, just assume any function. I would say it's x and this is fx. Okay, and suppose this is the curve. This is the fx. Okay, right? Possible some hypothetical example where there is the variable x and there is a function of x and the curve of this function is like this. Possible, like we have the function of MNC, but this is quite tricky function. Let's consider this. Let's consider this. So let's suppose we have a variable x and there is a function that represents that variable x. So the value of this function will change with every change in x, and let's suppose this is the curve of this function. Okay? Possible? Possible? Right. Now we need to see at every value of x there is some rate of change. So I would say if this is xi, right? So at this x there is some rate of change to this function, right? How this function is actually behaving? It's reducing. At this x value of x, I would say this is xj. At this point, the function will reduce by increase in xj. At this point, function will reduce by decrease in xj. Right? Right? So at every value of x, at every possible value of x, there is some rate of change in this function. Yes, guys? At this value of x, there is zero rate of change. Right? Right? So at every value of x, this curve have some rate of change, whether it's increasing, decreasing, or the zero, whatever it is. But at every value of x, this function have some rate of change. Right? Make sense? Yes, the tangent thing. So at every value of function, every value of x, this fx is having some rate of change, whether it's increasing or it's decreasing or something. But from x to xi, it's increasing, right? From x to xi, it's increasing, right? But at specific this value of x, it has zero. But if we just increase it a little bit, then it will say it's increasing, right? And this is also increasing. Okay? Okay? At specific x, it's 0. At this value of x only, this is 0. Right? If we see at this value of x, the tangent is 0. The rate of change of this curve is 0. Got it? What is this rate of change? These rate of changes are called gradients. These rate of changes are called gradients. And how do we calculate them? We calculate by d over dx of fx, right? Right? That's how we calculate, yeah, that's how we calculate these gradients. This is d over dx of fx. At a given value of x, we will see what is the rate of change in fx for a given value of x. Correct? Got the logic of gradients? Everyone, what are gradients? Gradients are just rate of change at a given value of x. Yes, guys? Perfect. Perfect. So now, after this, let's see how this will be applicable to MNC. But why can't we consider xi as increasing? We see it's increasing. If xi is increasing, the function is also increasing. If xj is increasing, the function is decreasing, right? Correct? Okay. Okay. Now let's understand how we can use this logic to get the best value of MNC. Okay. How we can use this logic to get the best values of MNC. Gradient is just the rate of change at a given value of the variable of that function. We have fx, we have x at a given value of x, how the fx is changing. That's the gradient. Okay, we have the fx, we have x at a given value of x, how fx is changing, that is what the gradient is. And in order to calculate this, we do the derivative. Correct? Yes, the gradient is the rate of change in a function fx for a given value of x. Fx is the function for which we need to calculate the rate of change, right? This curve belongs to fx. See, this curve belongs to fx. We need to calculate the rate of change in fx with respect to a given value of x. And that's what we are calculating right here. Fx is the function that has this curve. And for a given value of x, we want to calculate what is the rate of change, the magnitude and the direction. Right? Awesome. Awesome. Now let's see how we can use this. How we can use this in order to get the best parameters m and c in a linear equation. Okay. Now having this equation, plotting this equation will be quite tricky. So let's keep this simple example only. Okay. Let's keep this simple example only. Let's keep the simple example only. Suppose we have this fx, and this is the fx, and we need to get the value of x where this fx value is minimum, right? Similar like this problem, we need to get the values of m and c both where f, m and c is minimum. Right now consider we need to get the value of x where fx is minimum, right? Similar? Yes, guys? Similar? We just need to get the value of x where fx is minimum. We just need to look for that. Right? So first of all, we will pick some random value of x. First of all, we will pick some random value of x. I would simply say xr. Now there are lots of possibilities when it comes to the randomness, but let's assume the worst scenario. It picks the value of random x where we have the maximum error. Right? It picks the random value of x where we have the maximum error. Possible? We assume some random value for x and we got the we got the error, and that is the maximum error possible in x. Make sense? Awesome. Now we need to change the values of x in such a way that this value should reduce. Error is this fx. Error is the value of fx. Why we are saying it as error? Because this needs to be minimized. Right? Why we are saying it error? Because it needs to be minimized. Okay? The error is basically the fx. So we picked some random value of x, only some random selection, and we got the maximum possible value for the fx. But that needs to be minimized now. So now what should be the next steps? We should keep on changing the values of x to get the minimum value of fx. So now what we will do? We will calculate the new x. That will be x new. The formula will be xr minus learning rate d over dxr of fx, right? So what this formula will do, it will try to calculate a new value of x as per the rate of change in fx at a given value of xr, right? So it was reducing. If we increase the value of x, it was reducing, right? So it will definitely increase the value of x as per the rate of change and with some learning rate, so that this will be here somewhere, there will be new x value, right? And the function will move to this point. Make sense? Make sense? I'll explain what is the learning rate. This formula is the old value of x, that is the random, minus Learning rate, some parameter to identify how fast we want to train or how slow we want to train. Okay. This learning rate, just skip learning rate as of now. I'll explain learning rate in more detail. The old value of x minus the rate of change. Okay. The old value of x minus the rate of change. Make sense? Yes, guys. The old value of x minus the rate of change. So based on that, we can get the new x. To reduce this function, yes, U curve, because that's how it will be in case of these functions. We have different types of curves in neural networks where we work with the different complicated error functions. But right now with this function, we are going to have this convex curve, right? We have this convex curve when we talk about this kind of cost function. So we used to get this convex curve only. But when it comes to the deep learning and other complicated algorithms where we have different different types of error functions, and in that case we also have the problem of global minima and local minima. But right now in this function, in this curve, in this cost function, we used to get this convex curve. Okay. Why to reduce cost function? Anyone? Why to reduce function? Anyone wants to answer this, guys? Why do we need to reduce the function? We want to get the value, get the parameters that has the minimum error, right? Right? Okay. So we will keep on doing this thing. We will keep on doing this thing until it will reach at this point and the gradient will be 0, right? We'll keep on doing this thing until it will reach to this point and the gradient will be 0. We can call it as x final. Okay, that will be the final value of x, where the fx is minimum, and how we reach there from a random value of x by the help of its derivatives and rate of change. Okay, make sense? Yes, guys, make sense? Now see, what is this learning rate? This is a learning rate. Learning rate decides how fast we want to train or how slow we want to train. This is called learning rate. This is called learning rate. So if we keep it big, means it will take bigger steps. If we keep it small, it will take smaller steps, right? That's the learning rate, right? If we keep the learning rate big, it will take bigger steps to reach to the optimum value. If we keep it smaller, it will take the smaller steps to reach the optimum value. Got the concept of learning rate also? Yes, guys. The learning rate is how fast or how slow we want to train our model, right? If the learning rate is huge, so it will take more bigger steps to reach to the optimum value, right? If it is very huge, we need to take bigger steps to reach the optimum value. If this is small, we will be taking smaller steps. If it is small, we will be taking smaller steps, right? In linear regression, we don't specify learning rate, but when we implement the deep neural networks, we need to specify learning rate in gradient descent. But right now in linear regressions, we don't work with the learning rate. Okay. Got the concept? What exactly is the learning rate? It is just how fast we want to reach to the optimum value or how slow we want to reach. Now, if it's too big, we won't be able to reach the optimum point ever, right? If the learning rate is too big, we won't be able to reach the optimum point ever. And if the learning rate is very small, it's gonna take a lot of time. So ideally, we use the learning rate with the exponential decay rate function, exponential decay function. So as per the every change, the learning rate keeps on reducing and it reaches to the optimum point. But that is not the topic to discuss right now, because this is not something we need to do in linear regression. This is something we work while training the neural networks. We change the learning rate after every iteration. We decrease the learning rate after every iteration so that we can deal with the, exploding gradient and vanishing gradient problems. But that is something not we need to take care about right now. Got it? Yes, guys. Now we got the idea how exactly we calculate the values of M and C. Now this is a small example where we have one variable. In case of multidimensional, like we have M and C both, 3D gradient descent. Yeah, here it is. Let me show you a figure so that we can understand it better how gradient descent work in three-dimensional space. See this. This will be our function, okay? See this. What happened? Yeah. Now here we only have the function and one parameter that is impacting the function, right? That is x. The example we discussed, we have fx and there is only x that is causing the change in fx. But in our case, in case of linear regression, we have two parameters m and c that will cause the change in function, right? Here we have m and c both that's gonna cause the change in function. Yes, guys. The one we discussed, we only have x that causes change in fx. Here there is only x that causes change in fx. But in this equation we can see we have m and c both that are causing the change in function. Yes? Yes? So how this will happen? Like this. Now see, this is the cost function. Assume this is the function of m comma c, right? Suppose this is m and this is c, right? This is the curve. We need the value of m and c where this function is minimum. So we will calculate the derivative with respect to m and c both of this function, and based on that we will keep on modifying the values of m and c. Getting it? Are we getting the intuition of this? Yes, guys. Are we getting the intuition of this? How this will happen? Sure. Suppose this is function of m comma c, right? Okay. This is, let's say, m and this is, let's say, c. So we need to reduce this value by the changing values of m and c, and we can see the function is changing with every change in m and c both. We need to reach to the optimum point where this function m and c should be minimum, and whatever is the value of c and m, that will be our final m and c, right? And how do we do this? We will calculate the derivative of function m and c with respect to both c and m. Understood? Yes, guys. So that is how the linear regression will get trained. Now we don't need to implement all these mathematics and everything. We have a function that will do everything for us. We don't need to do any tricky coding for this. Not at all. We have the functions that can perform all these mathematics and everyone. By the minimum of cm will give the best linear line. No, not the minimum of c comma m. The minimum of function m comma c. We don't need to minimize the value of m and c. We don't want to minimize m or c. We want to minimize this function, right? We don't need to minimize the values of m or c. We need to minimize the value of this function. And what is this function? The overall difference between actual and predicted value. So the value of m and c that gives the minimum difference between actual and predicted value is going to be the best fit line. minimizing the difference between actual and predicted value, the sum of square of distances. Okay? Yes, please let me know what's your question. After we do this, what's our next step? I mean, after we got x and we can xn, x new, right? Now, once we have this new x, we will again do the same thing until we reach to a state where derivative is 0. We will keep on doing the same thing until this derivative reaches 0. What I meant to say, like this will go this way, then this, then this, then this, then this, and so on until it reaches at 0. So this will be, and this will be a stochastic process. This thing will be done multiple number of times until we have the derivative 0. Derivative 0 means it's a minimum value. See, here the derivative is 0 and this is also the minimum value of the function. The gradient, the derivative is 0 and also this is the minimum value. Awesome. It cannot go in opposite direction. It can never go in opposite direction because this change is happening as per the rate of change only. How we are getting this new x, that is with respect to the derivative, with respect to the change. So it can never go in opposite direction. Make sense? This can never go in opposite direction because the change in x is being caused by the derivative itself. So we can never go in opposite direction. It will always lead to the optimum value. That's why it's called descent. It's descending, right? Gradient descent. Descent here means descending. Got it, guys? Will go in the direction that gradient will decrease. Exactly. The new value of x will be only in that direction where the function is decreasing. That's why we have calculated the gradient, because if we have, if there is this possibility that it can go in any other direction, then we actually don't have a strategy in that case, right? If there is a possibility that this x or the value of function can increase with the new value, then we don't actually have a strategy in that case, right? Okay, now one possible step here is, see, let me again explain it in more detail. This 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 could be a possibility where, this could be a possibility where, suppose we have a quite bigger learning rate, we have a quite bigger learning rate. So we started from here, the next value is this, the next value is this, and the next value is this. Now see, at here it was decreasing, but the new value of x, it started increasing. Now it will again go in this direction. Correct? Correct? Again, see, if the learning rate is big, if the learning rate is big, started from here, went here, then it reaches here, right? Means it passes the optimum point. So at this point, the gradient was negative, but at this point, the gradient is positive. So now there will be decrease in the x. At this point, it will decrease the value of x, not it will increase. So far it was increasing because the gradient was negative, but now the gradient is positive. The gradient is positive, so it will decrease the value of x. Got it? Learning rate is actually we keep it small, 0.001. Ideally, this is a good, this is something called as a good learning rate. But right now, when it comes to the linear regression, we don't need to worry about the learning rate as of now, because this is a standard function. We don't have different types of functions in learning rate, different types of error functions in linear regression. When we work with the deep learning, there also this gradient descent has a lot of applications. In that case, we need to play with the learning rate also. But right now, learning rate is not a concern for us. It can go in infinite loop if there is a exploding gradient or a vanishing gradient problem. It can definitely go. If we talk about the gradient descent has this problem that it can go to infinite loop. But when we apply gradient descent with this kind of cost function, that is actually not a problem, right? If we only talk about the gradient descent has this problem of going into infinite. The gradient vanished or the gradient exploded. In that case, we will never be able to reach the optimum point. But when we implement this gradient descent with this cost function, specific linear cost function, this is not a problem, right? Yes, guys, understood? That is actually a problem in chain rule of differentiation. That is a problem of getting into a infinite iterations in chain rule of differentiations. Okay, perfect. All good with the entire process of linear regression, guys? Awesome, awesome. Now let's talk about its problems. What can happen and how to deal with that. So the problem basically is of overfitting. We might get a overfitted model. Okay, we have space. Yeah, we have space here. So let's discuss the overfitting right here. Okay. Now, for example, let me again create a sample plot. Okay, suppose this is the data. Okay, suppose this is the data. The best fit line, if you try to plot, it will create, I would say this will be the best fit line. Yes, X, Y. This will be the best fit line, right? But if we see, this line is actually still having a lot of error. So we can add some polynomial feature, and we can actually add a curve, curve kind of thing, and that can be more accurate than a straight line. Yes. If the straight line is not actually giving a good result, it's still having a lot of errors, we call it as a underfit. And if we add some polynomial feature, we can include some curve feature in our predictions. So we are going to get more accurate, right? Possible? No, we will create a new feature. Right now we use X to predict Y, but let's suppose we started using X comma X square to predict the Y. Okay. In this, we only used X to predict, but now we used X square to predict Y. Right? X and X square both. Let's say we used X and X square both to predict Y. So there will be some curve in that case. We just included one more polynomial feature. Apart from x, we used x square also, and then we have the curve like this. Make sense? Okay. Now, also there could be a case where we get a function that is over optimized, a line that is approximately going to every point, this yellow line. Yeah, it can become non-linear too. Yes, it can definitely become non-linear too. Okay, now this is also a possibility, guys. This is also a possibility. We can also get this, and we are going to get a brilliant accuracy in this kind of line. In this zigzag kind of line, we are going to get a brilliant accuracy. Yes, guys? But see, this line will not be able to perform on unseen data. This line will not be able to perform on unseen data, right? Yes, this line is performing brilliantly on the given available training data, but not necessarily that we are going to have the same zigzag curve, and we might have a lot of error in testing or in unseen data. Possible? In the case of yellow line? Yes, yes. I mean, we can say it's not a generalized model, right? Generalized model is the one that gets the ideal accuracy in train and test both. So we can say this yellow line is not actually a generalized model. Yes, because it is giving a good accuracy in training, but it won't be able to give that good accuracy on another data set, unseen data. Make sense? But the green one is actually giving the best accuracy. So to conclude, the green one is the best fit, right? The yellow one is overfit, and the black one is underfit. Okay, so best fit, this is what we call as a best fit. Then this is what we call as a underfit, and this is what we call as a overfit. Means it has been overly trained. Yes, no, it's not a moving average, it's a best fit line, but it's this best fit line is actually overtrained. The best fit line is actually overtrained, means it is the amount of cost function is being over optimized in the case of the yellow line. So it is giving a good accuracy in training, but it won't be able to give a good accuracy in unseen data. Make sense? Make sense, guys? Okay. Okay. Now we got the idea what exactly is the overfitting. Overfitting is a case whenever cost function is over optimized. It has been reduced more than enough. So the model is actually giving a good accuracy in training and the available data on which the model has been trained on, but it won't be able to give the good accuracy on unseen data, on a new data set. Yes? Getting it? The case of overfitting, the best fit is something what we want. In case of underfit, actually, this is not a fault of regression. This is not a fault of optimization technique or something. We don't have the enough data, or we need to do some feature engineering to deal with the underfitting. But if it is a overfit, this is a concern in optimization. The models, the parameters are over optimized, right? So the best fit is something what we found. Underfit is actually not a problem of optimization technique or the linear regression training. It's not a problem. This could be because of limitation of data, or the data do not have a linear relationship. We are looking for a line and data is not actually having a linear relationship. So the underfit is actually not a problem of linear regression. Yes? Underfitting is not a problem of linear regression. We can't blame linear regression for underfit model. We need to play with the data pre-processing. We need to play with the data set and other things to deal with the underfit model. Best fit is what we want. Overfitting is something that can be caused by over optimization of the cost function, right? So this is actually a problem and we need to look for a possible solution in order to deal with this problem, right? Understood everyone about overfitting, underfitting and best fit model? Awesome. Awesome. Okay. Now let's understand the actual cause of overfitting. So actual causes, we understood overfitting is caused because of over optimization of the error function, the cost function. In overfitting, the cost function is being over optimized, right? And let me show you the cost function. Yes. In cost function, in overfitting, we can say the cost function is over optimized. That's why overfitting is caused. Overfitting is caused by over optimization of cost function. Yes, this makes sense. This makes sense. The overfitting is caused because of over optimization of cost function. And if we look closely, the cost function, this will be summation of I equals to 0 to n yi minus m xi plus c whole square. And in case this is for linear regression, this is basically for linear regression only. Linear regression. In case of multilinear regression, we have multiple x, so the cost function would be like cost equals to I equals to 0 to n yi minus, now prediction will depends upon all the values of x, m1 x1 m1 x1 plus m2 x2 plus m3 x3 m3 x3 right, and so on plus c. That will be the case in case of multilinear regression model, where we have multiple inputs to predict the target variable square. Yes guys, to predict we are using x1 x2 x3, multiple x are there, so there will be multiple n's also. Make sense? Multilinear regression, so this is going to be the cost function in multilinear regression, this is going to be the cost function in single linear regression. Yes, let me know if anyone have any confusion in this. Please let me know if there is any question, any doubt, any confusion about this, please. No confusion? Everyone is clear? Perfect. Now, we understood it is caused by over optimization of the cost function, and if we observe the cost function, it is inversely proportional to the magnitudes of m. If the magnitude of m will get increased too much, the value of cost function will decrease too much, right? Cost is actually inversely proportional to magnitudes of m. Right? If the magnitudes of these m will increase, the difference will decrease. Yes, guys? If the magnitudes of m will increase, the difference will decrease. Yes? This will cause the cost function to decrease. Yes, this will cause the cost function to decrease. right? Okay, is this thing is clear? The real problem, the actual cause of overfitting is high magnitudes in M. Okay, if the values of M1, M2, M3 will increase, the difference will decrease. Yes. Ultimately, the cost function will also decrease in that case. Difference is the cost function, means the magnitudes of M are increasing. This is causing the decrease in the cost function, right? Got it? So actual, we can say that the real cause of overfitting is high magnitudes in M, right? High magnitudes in M is actually causing the overfitting. Right? What if it goes beyond IY value? I'm sorry, not already bigger. If it is already bigger, it will increase, more difference will increase. I'm sorry, I didn't get this thing. If it is already bigger, you mean to say the cost function is already bigger? Then the M, if the value of M is already bigger, sorry, I'm so sorry. If the magnitude of M is bigger, so increasing it will increase the cost function. You're trying to say this. That will be the case if the direction is negative. Got it. That will be the case if the direction is negative. If it is minus M, that will be the only case when the relationship is negative, right? Yes. The increase in value of M, increase in magnitudes of M will only increase. Actually, it will not increase, it will decrease only, but that could be a case where the magnitude is negative, right? That will be the case where magnitude is negative. Okay, let me use some hypothetical numbers here. Suppose y is 150, right? Right? And y predicted is 130. Suppose y is 150, y predicted is 130, y minus y predicted is positive number, right? Y minus y predicted is positive. Yes? Yes? So we are sorted in this case. The increase in M, if the value of M in increase, so M will also be positive. M will also be positive. Increase in M will decrease the difference. Sorted? Yes? Okay. Now the another use case where Y is 130 and Y predicted is 150, right? Now Y minus Y predicted is negative. Y minus Y predicted is negative, means there is a negative correlation. We need to decrease. So M will also be negative. Yes? M will also be negative in this case. Yes, guys? Make sense? Does this make sense? The M will also be negative in this case. Now, if you increase the magnitude of negative M, this M is actually decreasing in that case. And the prediction Y will decrease, it will get more closer to the actual Y and the difference will also decrease. Again, minus M, we are increasing the magnitude of M, let's say minus 2 and minus 4. This is actually decreasing. The magnitude is increasing, but the overall value is decreasing, right? The magnitude of M is increasing, but the value of m is decreasing here. Yes, guys? We are increasing the magnitude of m minus 2, minus 4, 2, 4. The magnitude increased, but the value of m is decreasing, right? And this will decrease the predicted y. This will cause the decrease in the difference. Means increase in magnitude is actually causing the decrease in the cost function. Getting it? Yes, guys? Getting it? Yeah, we are also squaring. We are definitely, we are also squaring. We are also squaring. But they're squaring, we are actually squaring this thing. But we are trying to understand that increase in magnitude of m will ultimately decrease the cost function. Yes, we are squaring. Yeah, definitely we are squaring. The difference is actually decreasing. Like what exactly we are trying to say is the difference is ultimately decreasing. The question was, what if increase in m can cause the increase in this difference? For example, I would say that is about this difference, guys. That was about the difference. See, that is about the difference. But the relationship, the direction of relationship will exist. Wait. Let me explain, guys. Let me explain. We are squaring this difference. We are actually squaring this difference. Okay, we are squaring this difference, right? But if it is negative or positive, will decide what's gonna be m. The negative or positive will decide the value of m, right? If the difference is positive, m is going to be the positive. If the difference is negative, m is going to be negative, right? We are not squaring m, we are squaring the difference, but whether they are positive or negative, that will decide the direction of m. Yes, guys? That will decide the direction of m. Yes. What I meant to say is, again, if it is y equals to 150, y predicted is 130. Okay. Another case, y equals to 100, y predicted is 120. Okay. Now, if we increase y predicted, like if we increase it to 130, so the difference is increasing in this case, right? Even if it is negative, we square it, but the overall difference is increasing. Yes, we calculate the square of difference, but it is increasing from here to here. Yes, guys? Y minus y predicted square is increasing here, right? So we should reduce it. 110 or 100, we should reduce it. How we will reduce it? By having negative m's, right? We should reduce the we should reduce the predictions. And how we are going to reduce? By having a negative value of m. Yes? Got it? What I mean to say is, higher in the magnitudes of m will lead the over optimization in the cost function. Right now we are just trying to understand the magnitudes of m are inversely proportional to the cost function. Higher will be the magnitudes of m, be it minus m or plus m. The magnitude of m will cause reduce will cause the reduction in cost function, right? It's not possible that increasing the magnitude of m will increase the cost function. By this way, we saw it's not possible that increasing in magnitudes of m can increase the cost function. Understood? M is positive if m Then if M increase, then Y prediction will increase. Cost function will increase if wait, Y predicted Mx plus C. If M is positive, then if M increase, Y prediction will increase. If M is positive, in Y equals to Mx plus C, if M is positive, then if we increase M, Y pred will increase. Okay, yes. And then Y actual will be greater than Y prediction, the cost function. That cannot possible because that's what we discussed in the gradient descent. That cannot be possible. If it will reach to that point, it won't go further. It will come to backwards, right? Yes, it cannot go further then. If right now it is increasing, but it will never go there. It will come backwards, right? Yes. At this point, we can say increase in cost is actually increasing in the magnitude of this will increasing in cost, but this will never happen. It will never going to increase it. Okay, if this thing is clear that the higher magnitudes in M will cause the reduction in cost function. Is it clear? We will talk about that, what we will do after this. Is it clear the increasing in the magnitudes of M will cause the reduction in cost function and the cause of overfitting is because of high magnitudes in M, right? This thing is clear, everyone? Magnitude of M increases, cost function is decreases because both are inversely proportional. Then the cost function is decrease, the overfitting chances increases. Exactly, exactly, exactly. Right. So like overall ultimate the conclusion of this is increase in the magnitudes of M will cause the decrease in the cost function, and the this overfitting is because of over optimization, means higher magnitudes in M is actually the cause of overfitting, right? Okay, guys, this part we try to solve a question. If you don't understand this, don't worry. We understand this part that increase in magnitudes of M is causing the decrease in cost function, and ultimately higher magnitudes of M is the cause of overfitting. Is this thing is clear to everyone? Yes. This thing is crystal clear to all of us that higher magnitudes of M is causing the overfitting. That's it. Okay. Now we'll talk about the solution after the break. Just keep this in mind that higher magnitudes of M are causing the overfitting. So we need to restrict to get them higher. We should restrict the magnitudes of M to get higher. And there are possible methods to do that. We will talk about those methods after the break. Okay. So as of now, we discussed the linear regression. How do we train linear regression? How do we calculate M and C, right? And we talked about a possible problem that is overfitting, and we also understood that overfitting is caused of because we have the higher magnitudes in M. And now we will see how do we deal with that. Yes, guys, good till here. Yeah, we'll take a break. How to register other module which is full. Other module regarding which module? Okay, Tableau and other things. In that case, you need to get in touch with some counselor. And yeah, I hope the help and support will also work. Okay, now are we enjoying this algorithm part? Yes, guys, is it fun? Perfect. And let me tell you, all these, yeah, we need to understand the maths only. All these mathematics, what we are discussing, that will be done with a single line of code. Everything will be done with just a single line of code. Okay. So the coding will not be that much tricky, but we need to understand what's happening behind that, function. Yeah, I'm just uh, placing the timer. Google timer. Okay, 20 minutes. Let's get back after 20 minutes, guys. Hey everyone. So we are all back now. Perfect. Now let's see how do we deal with this overfitting concept. Okay. Now this overfitting, like if we need to restrict magnitudes of cost function to get higher, right? The solution here is the magnitudes of cost function. We should restrict the magnitudes of cost function to get higher. That's the possible solution, right? Perfect. So how we actually do this? This term is called L1 regularization. And in this case, we actually try to update the cost function. So in case of L1 regularization, the cost function will become summation of I equals to 0 to n yi minus m x1 plus m2 x2 plus so on plus c whole square plus this is a penalty factor alpha of I equals to 0 to d magnitudes of m, where b is number of predictors, means the number of input variables. Okay, now see what we did. We added a penalty term. We added a penalty term to the cost function. Now that this relationship of inversely proportional does not exist anymore. The increase in magnitudes of m will increase the cost function now, right? Because now we are adding the sum of magnitudes of all the m to the cost function. This way, if the magnitudes of m will increase, the cost function will also increase, and the gradient descent will not, it will never let the magnitudes of m to increase. Make sense? Sure. If we see here in this cost function, we added a penalty term. And what is the penalty? The sum of magnitudes of all the m's, right? It is mi. The sum of magnitudes of all the m's. Now, if the magnitudes of m increases, the cost function will also increase. Alpha is a regularization factor. We'll explain alpha. I'll explain what is alpha. As of now, does this make sense that by adding this penalty, the inversely proportional thing is not there anymore, right? This inversely proportional thing is not there anymore. Yes, because now if the magnitudes of are increasing, the cost function is also increasing, right? So the gradient descent will never let the magnitudes of m to increase, and this can deal with the overfitting to some extent. Yes. Now this alpha is the regularization parameter, and this alpha helps us to decide. This is what we need to give in this case, right? This alpha is a regularization parameter, and this way we need to decide what amount of penalty we need to add, right? In this alpha, we need to decide what amount of penalty we need to add. Either like entire penalty 0.5 means 50% of the penalty, 0.1 means 1% of penalty. So what amount of penalty we need to give, that is something we decide by this regularization parameter alpha. Okay, this algorithm is called lasso regression. This is called lasso regression. Okay, clear? Yes, guys. Lasso regression is clear. Okay, now the another form of regression is ridge regression. We call it L2 regularization. This is called ridge regression. Okay. So what happens in this case? The cost function will be the summation of I equals to 0 to n yi minus m1 x1 plus m2 x2 and so on plus c whole square plus again a regularization factor alpha I equals to 0 to d. Here we will be using square of sum of square of magnitudes. Here it was magnitude, here it is square. That's the difference between ridge and lasso only. The small difference, the penalty is having the sum of magnitudes. Here the penalty is having sum of squares of n. Okay. Yes, exactly. Alpha is how much we want to regularize. Exactly. Easy? Perfect. Anyone any questions about the regularization? Then we will talk about the difference in L1 and L2 regularization. When we should use L1, when we should use L2. And there is one more that's called elastic net. Exactly. Regularization to avoid overfitting. Awesome. Yes. Alpha is the regularization parameter, what amount of penalty we need to add, right? So alpha will see how much we want to regularize. If we give alpha 1, we are adding the entire penalty. If we give alpha 0.5, means we are adding 50% of the penalty. So alpha is that. Okay. Interesting. Yes, guys. This linear regression is something interesting. Ridge and lasso is also clear. Regularization L1 and L2 clear, everyone. Awesome. Perfect. Now let's understand what is the difference in L1 and L2 regularization. So first of all, let me tell you that L1 regularization or the lasso regression can eliminate the irrelevant features, right? L1 L1 regularization or lasso regression, this can eliminate the irrelevant features, right? But L2 regularization or rich regression cannot do that. In L1, it can remove the irrelevant features by itself, but L2 cannot. The L1 regularization technique, that is the lasso regression, can remove the irrelevant features, but L2 cannot. I'll explain how. So, in L1, the values of M can lead to 0. In lasso regression, the values of M can achieve this value of 0. They can, it's a possibility that M's can get 0 in case of lasso. But in case of ridge regression, it's not possible to have any M as a 0 in case of ridge regression. That's how lasso regression can eliminate the irrelevant feature, because there is a possibility to get the value of M as 0. But in ridge regression, it's not possible to get the M0. So that's the difference. How is it possible? We got this idea what exactly we are talking about. That in lasso regression, the values of M can be 0, but in case of ridge regression, it's not possible that the value of M can be 0. Right? How? I'll prove it. Like, there is some mathematical, notations. I will prove how this happens. But are we good with what exactly we're talking about here? Yes, guys, are we good with what exactly we are talking here? In case of ridge, the values of M can never be 0. In case of lasso, the values of M can get 0. Okay. Now let's take a hypothetical example. Okay. Let's take a hypothetical example where we need to predict Y with the help of variable x1 and variable x2. Okay. Assume. And we know Y is approximately equals to 2 times x1. Y is also approximately equals to 2 times x2, and x1 is also approximately equals to x, or let me use this one. Y is also approximately equals to x1 plus x2, right? Assume this is a case here. Assume this is the case. Okay. We need to predict Y with two variables x1 and x2. Okay. Assume this is the case right now. This is a specific hypothetical example where we need to predict Y with the help of two variables x1 and x2. Now we know Y is approximately equals to 2 times x1. Y is also approximately equals to the 2 times x2. And Y is also approximately equals to the x1 and x2. Make sense? That is our case. That is our example. Okay. Now if we write equation y equals to m1 x1 plus m2 x2 plus c, right? So the possible values of m1 and m2, this is 1, it looks like x mod. The possible value of m1 and m2 can be 2 0, 0 2 and 1 1. Yes, these are the possible values of m1 and m2 if this is the case, right? Okay, now let me remove lasso from here. Okay, understood. This example is clear. This example is completely clear, everyone. This is the case, and as per this, the possible values of m1 and m2 can be 2 0 0 2 or 1 1 only, right? Nothing else is possible. Okay, now let's see the penalty in ridge and lasso. What will be the penalty in ridge and lasso? Okay, penalty in case of ridge and in case of lasso. Okay, So in case of Rich, it's gonna be m1 square plus m2 square, right? m1 square plus m2 square, but in case of Rich, it will be mod of m1 plus mod of m2, right? That's gonna be the penalty for Rich and Lasso. Okay, now see there's the penalty. It will be 4. It will be 4 and it will be 2. Yes, these will be the possible penalties, and here it will be 2, 2 and 2. Right? These are the penalties for Ridge and Lasso. Yes, guys, understood? 4, 4, 2 for 2, 0, 0, 2, 1, 1, and 2, 2, 2 for Lasso. Okay, now see the gradient descent uh, in case of Ridge, it will always go with this. In case of Ridge, it will always go with 1, 1. Yes, it will never go with any of these two values because it wants the minimum penalty. Penalty should also be less. The Ridge regression, if it is a Ridge regression, if it's a L2 regularization, the gradient descent will always go with this one, 1 and 1. Yes, but in case of Lasso, it can use any of them. In case of Lasso, it can use any of them. And in case of Lasso, it is 67% chances that it will remove one insignificant variable. Right? I should write it at the place of Lasso. In case of Lasso, there are 67% chances that it's gonna repeat and it's gonna remove any of this x1 or x2, because out of three chances, there are two chances where one variable will be eliminated. Right? Lasso can pick any of these values. Lasso can pick any of these values, right? And in two of such outcomes, one variable is being eliminated, right? So Lasso can actually eliminate the insignificant variables, but Rich cannot do that. Lasso can eliminate the insignificant variables, but Rich cannot. Correct? Why so? Yeah, that's why we are saying it can. That's why we are not saying it will. Right? That's why we are saying it can, but not it will. Yes, in which we will be using the combination of M1 and M2 where we have the minimum penalty, that is 1 comma 1, right? So if we use M1 and M2 as 1 1, X1 and X2 both are utilized. If we use M1 and M2 as 1 and 1, no, Reg is not eliminating. What exactly is the elimination here? The variables x1 or x2. We need to eliminate x1 or x2 here, right? We need to eliminate either x1 or x2. So if the reg is choosing 1 cross 1, x1 and x2 both are being utilized. Yes. If you use x1, m1 and m2 as 1 and 1, so x1 and x2 both will be utilized. Both are being used. But if you use 0 2 or 2 0, one is being eliminated because m is 0. If the m is 0, the x will be inactive. If the m will become 0, the x will be inactive in that case. Means it's not significant at all. Yes, guys, are we getting it? In case of lasso, anything is possible. 2002 or 11. Yes? In case of lasso, anything is possible. 2002 or 11. So if it is using 20 or 02, one of the variable will be eliminated. If it is 20, M1 is 2, M2 is 0, then X2 is not active at all. X2 is insignificant in that case. If it is using M1 as 0, M2 as 2, in that case, M1, X1 will become inactive. There is no use of X1. So Lasso has this capability of removing insignificant variables, but that is something Rich cannot do. Make sense? Awesome. The approximation here, the approximation here will be cleared out by the C. We have the approximation means they are not actually equal, so that approximation will be taken care by C. Yes, this approximation will be taken care by C. Rich. Okay, now apart from this, what do we understand? What exactly is the difference in rich? The penalty is big. Yes, the penalty is big in case of rich. Good question. Why should we use rich? The penalty here is big in comparison to lasso. Yes, guys. So if the use case, if there is a such use case where overfitting is very extreme, alpha value is something what we specify. Alpha value is something what we specify, right? Okay, in case the overfitting is very extreme, means there is a huge difference in train and test accuracy. If there is a huge difference in train and test accuracy, a very huge difference in train and test accuracy, we can go with the rich in that case. We need high penalties. Yes, guys. There is a huge difference in train and test accuracy. If there is a huge difference in train and test accuracy, that means there is an extreme case of overfitting, and in order to deal with that, we need something big as a penalty, right? The values of magnitudes should be limited in a very smaller constraint. The value of the magnitudes of the coefficient should be constrained into a lesser lesser range. Make sense? Okay, in simple words, guys, in simple words, I'm making it more tricky. In simple words, the intensity, how intense the overfitting case is. If it is very, very badly overfitted, go with the rich. If it's quite not, it's not that intense, go with the last one. Easy, right? Awesome. One last thing to discuss is the evaluation methods. Okay. One last thing to discuss is the evaluation method. How do we evaluate a linear regression? Now we will be talking about the different types of matrices, R square, adjusted R square, MSE, MAE, MAPE, and all those things. Yes, definitely. We'll see application of every algorithm what we have covered today. Okay, yes, guys. All good till here. So now we can talk about the evaluation methods. How do we evaluate a linear regression? Oh, yes. Okay, sure. Elastic net is actually the combination of elastic L1 and L2. In case of elastic net, the cost function will be plus alpha of plus lambda. Yes, that's the elastic net regression. That's the elastic net. Okay, now how exactly it's looking like? Yes. How is it looking? Combination of both, right? Where we have two regularization parameter, one for the penalty of L1, one for the penalty of L2. So if we make alpha 0, we can implement both using elastic, right? We can implement both using elastic. Make alpha equals to 0, it's rich. Make lambda equals to 0, it's lasso, right? Easy? Easy? Yes. Yes. So elastic is just the combination of both L1 and L2. Some worse scenarios where neither L1 is working, L2 is working, so we can often try the elastic net. Okay. All types of penalties we are adding. Alpha and lambda lambdas are user defined. We need to specify the regularization values. So if alpha is 0 and lambda is greater than 0, it is rich, right? If alpha is greater than 0 and lambda equals to 0, it's lasso. Yes? No, we try to keep the alpha and lambda as positive only between 0 to 1. And like in the practical cases, we always keep it in decimals, right? The values of alpha, we mostly try to keep it in decimals. Awesome. Now let's see the evaluation. How do we evaluate a model? whether it's accurate or not. Is it clear, everyone? The regularization, linear regression, fitting, training, everything is good. Okay. Now in this evaluation, how there are basically two matrices, R square and adjusted R square. So first of all, we have R square, R squared. This is also referred as R2 score, right? It's the same thing. This is equals to 1 minus, sorry, y minus y alpha, y minus y predicted whole square divided by y minus y average whole square, right? Where if this is the data point, this is y predicted, and another line is y average, that is the average of y average, right? And what exactly this R squared returns, what exactly it's trying to tell, the amount of information our model is able to explain in the target variable. So if the R square value is 0.6, means model is 60% accurate. If the R squared value is 0.9, it means the model is 90% accurate. So R squared is basically telling us what amount of information our model is able to explain, what amount of information our model is able to explain in the target variable. If the R square value is 0.6, means it's 60% accurate. If the R square value is 0.9, means it's 90% accurate. Means 90% of the information in target variable is being explained by a best fit line. A best fit line is capable enough to explain 90% of the information in target variable, or what amount of information it is explaining. That is what R square will tell us. Okay. Yes. Got it, guys? The R square. Nearing 100% will be more accurate. But targeting variable is what we need to predict. If we want to predict sales, then it's a sales is a target variable. R2 equals to 1 is a perfect fit. MSE, mean squared error, is different. Mean squared error is another error function to evaluate. MSE, mean squared error, is another evaluation. Is basically an error function that can tell us how better the model is. Mean squared error. Just the cost function here, we are calculating the sum. If we calculate the average of this, that's the MSE. The definition of R square, we can simply say R square is basically the amount of information the best fit line is explaining in a target variable, right? Amount of variance our best fit line is explaining in the target variable, or what amount of information our best fit line is explaining in a target variable, that is R squared. Okay. R square formula with MSE. I'm actually not sure about R square formula about with MSE. What is MSE? MSE is mean squared error. So this is the sum of square errors. If we calculate the average of square errors, that's called MSE, and it's better to have less MSE. And instead of MSE, there is also one other cost function, one other error function, that is called mean absolute percentage error. That's the more easy to interpret error function. It will tell us what percentage, absolute percentage of error is. MAPE, mean absolute percentage error. Okay, so clear guys, R squared everyone, what is R squared? The formula and what R square, what we interpret out of this R square value. Clear? Now, apart from R square, we also have adjusted R square. Adjusted R square. Uh, for the evaluation, we don't need. For the implementation, we don't need. But in interviews and all, this could be a question. 1 minus R square n minus 1 divided by n minus p minus 1, where p is predictors and n is number of samples. Yes, R square is for the regression model. Okay, now let's see the adjusted R square, where we also have the value P in this case. P is the predictors, the number of predictors we are using, right? P is the predictor, the number of independent variables we are using, right? Yes, now let's understand the formula of adjusted R square. We remember the concept of significancy and multicollinearity, guys. Remember the concept of significancy and multicollinearity? Okay. So if we remove some insignificant column, if we remove some insignificant column, in that case, R square will not change, but P will decrease. If we remove some insignificant column, in that case, R square will not change, but P will decrease. Yes? N is the number of samples we have. N is the number of samples we have. Yes, guys. In this case, if we remove something insignificant, the P will reduce, but R square will not reduce. Now tell me, what will be the change in adjusted R square? Will it increase or decrease? It will increase, right? But if we remove some significant, it's gonna decrease. If we remove something insignificant, the adjusted R square will decrease. Right? Sure. If we remove some insignificant column, if we remove something insignificant from the data, the R square will not change, but the value of M will decrease. Yes, guys? So ultimately, the adjusted R square is going to increase in that case. we should not consider insignificant. It like a good prediction model is the one that is optimized, efficient also. Means there should not be any insignificant columns, insignificant predictors as our input column, right? So if we remove the insignificant columns, the R square will not change, but the P will reduce, and ultimately the adjusted R square will improve, right? So, like what exactly adjusted R square is telling us, it is also telling about the significance in the model. Yes, guys, adjusted R square is also telling about the significance in the model. So we have two matrices, R square and adjusted R square. It's not understood, sorry. Now it's understood? Clear? Okay. Awesome. Is it clear? Perfect. 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 Yes, guys. Now that was everything about the linear models, linear and multilinear regression. So tomorrow we'll do a business case in order to solve the linear regression, right? So before that, let me just show you the file and everything so that we'll stay prepared. Everything is on the go. We can just download the files and whatever is required. Let me upload everything, and we can keep the environment all set to start with the coding. Okay. Okay. Today is day 6, right? So in day 6, I need to upload this whiteboard. And I think, yeah, we haven't referred any code yet. Let me upload the code files and everything for today itself. No, we don't have enough time to start the coding part. So let me upload so that tomorrow we can get started. Yeah, the difference in R square and adjusted R square is basically about the number of predictors and the samples. It will also take care about the significance. Okay, so today's code part I have uploaded plus linear algos, guys. Please download and download and configure all these things for tomorrow's class. We will be doing Big Mart Sales V2 tomorrow. Okay, so let's stay prepared for tomorrow. Is it okay to finish one algorithm in 2 days? Yeah, it's okay. No, not a big deal. So okay. Because see, actually, this is the first algorithm what we are doing, right? This is the first algorithm what we are doing. So we need to understand the flow first, right? Now, once this is clear, the programming pattern is clear, now we can speed up after this, right? Once we got the entire logic for the first algorithm, we'll see the business case. Once everything is clear, then we can definitely speed up. And we are good with the pace, guys. Perfect. So I have updated everything in day 6. Tomorrow we will do the linear regression and I will share you some more case studies on linear regression to explore and practice. And we will also talk about the logistic. If we get time, we will also talk about the concept part, the mathematical part of logistic regression, and we'll do its coding day after tomorrow. Right? Or the logistic is not a very huge, this is something we can do in one day itself. So let's see if we can do logistic tomorrow or day after tomorrow, it will work. Logistic will not take much time. We can do logistic in one day itself. Yes, we are, that's it for the day. If there is any questions, anything, anyone, yes guys, we are open for the Q&A. If we are all good, we can drop off. Yeah. Yes, guys. Let me know if anyone have anything to ask. Yes, please. About PC and LDA, please. How do we check homoscedasticity in linear regression model? We'll talk about the homoscedasticity and heteroscedasticity both in more detail actually. Let's do it with everyone. We'll talk about homoscedasticity and heteroscedasticity. We will talk about that in more detail tomorrow with the data set. Okay. To go to the more details, can you recommend a good reference to study maths? There is a website, Math is Fun. If you want to understand the individual concepts, you can simply refer to Math is Fun. Math is Fun. Okay. There is a YouTube channel, StatQuest. They also explain statistics in very, fun way. So you can also refer to the StatQuest. Math is Fun and StatQuest. Suppose we have 1000 columns, we perform PCA or LDA, and it comes to be 500 columns. This is also huge. Then again, do we need to perform? No, we cannot perform it again. We cannot perform it again. That PCA, that like if we got 500 columns, this is what we can have the best at its best. From the Friday session, if PCA we applied for the standard scalar, can standard scalar be applied to not? Yeah, exactly. Good question. And this is something we also discussed while discussing the standard scalar also, right? So when we discuss the standard scalar, we talked about this thing that standard scalar needs to be implemented only when the data is normally distributed. But if it is PCA and LDA, we only do the standard scaling itself, right? In case of PC and LDA, we only do the standard scaling because the ideally standard scalar will make the data centered to 0 with the standard deviation close to 1, right? So it's always whatever is the data distribution, we always do standard scalar to before we implement the PC or LDA, right? We will always do standardization before we do PC and LDA. That's because the standardization will make the data centered to 0 with the standard deviation close to 1. So any population type is okay to apply standard scale only if we are using PCA or LDA, right? Only for the PC and LDA. Okay, apart from PC and LDA, there is one more feature engineering technique, guys, factor analysis. No, actually, see, in case of PCA, it will be more helpful if the data is centered to 0, right? So that's why we use standard scalars for PC and LDA. There is one more type of feature engineering technique called feature factor analysis. Factor analysis, guys. So you can definitely explore about factor analysis. We all have that drive link what I have shared. In that there is a file that has all feature selection techniques. I think we have talked about that notebook file where there is a lot of feature selection techniques, right? Oh, no, I think we have talked about the one for different pre-processing methods. Okay, let me give you one more interesting file to explore. So if you will go to this drive link, if you will go to this drive link, we talked about PCA and LDA, but apart from PCA and LDA, there are some other feature engineering techniques also. Feature selection techniques. Here it is a file feature selection techniques.ipynb in this simply learn ML content. So try to explore this file also. This has different feature engineering techniques apart from PC and LE also. Okay, chi-square. We have the chi-square. We have the ANOVA. We have forward elimination, forward selection, backward elimination methods. So there are different methods for selecting features in this feature selection techniques. X has 784 columns where fit has 300 and how this okay in transform X transform fit has 331. I'm sorry, the fit is a function. Fit cannot have actually I didn't get this code syntax. X transform X standard X stand. Okay, from Friday session, the the codes are either it will be dot fit transform, either it will be dot fit or dot fit transform. Sure, wait a sec. Yes. Okay, here it is. Let me scroll it. Yes, tell me. Yeah, this is the PCA code. Three 40. Okay. Yes. And transform as 331 columns. That's your question? Actually, this is what we want to achieve. What is the overall goal of PCA? Why we do PCA? Yes. Why exactly we do PCA? To reduce columns, right? So fit transform is reducing the columns from 784 to 331. Yes. Yes. Does this make sense? We had 784 columns and PCA reduced it to 331, right? we don't eliminate or select the columns in PCA. We have discussed it many times in PCA and in LDA. It will not select or drop any column, right? In X transform, we are giving, see, this will transform the standardized data. We know how the PCA works. It will take the data, it will generate the principal components, and it will select those number of principal components that have 90 to 95% of the explanation in the data. So we did the fit earlier and we observed 331 principal components are enough. So while creating a PC object, we specified number of components equals to 331, right? So when we transform, it will generate 331 columns only. Okay. Make sense? Yeah. Sure. So we calculated the cumulative variance on explained variance ratio. So do we know what is explained variance ratio? What is this plot? Yes, do we know what exactly is this plot returning? Explained variance ratio? Yes, does this, what exactly is explained variance ratio? Is it clear? Or if I show you, yeah. Now what are these values? Do we know what exactly are these values? Percentage of variance explained by each principal component, not the column, by each principal component, right? Now, we calculated the cumulative sum of variance percentage for the group of principal components, and we try to extract how many principal components are explaining 95% of the variance. Yes? Cell number 338. Now, what exactly we are trying to do? We are trying to see the number of principal components till where we have the cumulative sum of variance percentage till 95, right? If I pick some random numbers here, suppose 1, 2, 3, 4. Okay. So the variance percentage is 0.5. Suppose 0.5 is very huge. 0.2, 0.1, 0.8, 0.5, and so on, right? Now the cumulative sum here will be 0.2, 0.3, it should be 0.08. My bad, I'm writing anything. It should be 0.8 and 0.4, right? 0.5. So 20, 30, 0.34, 0.39, right? So like this it's going. If we want to count till the number where it is less than 0.95, till it is less than 0.95, we will get the count of principal component that gives the 95% of variance. Yes? Just keep on going until this cumulative sum is less than 0.95. We will get the number of principal component that can explain 95% of the variance. Yeah, sure. Wait. Let me unmute you. Yes.
Am I audible?
Yeah, you are audible.
Okay. My question is basically it's kind of a slicing, right? So in pandas, when we apply, um, say if you want to filter it out some column with the values, then we
Mm-hmm.
specify the column, first the data frame, then in the square bracket we mention the column, and then the
Mm-hmm.
value what should be less. So here
Mm-hmm.
my question is basically here we say as var percentage, and again we put this to the same var per and then less than 0.95. So exactly which column it is getting into this, or it is just a series data and we are reducing it.
Var percentage is actually an array. If I show